Now let's talk about nuclear fusion reactions. In a nuclear fusion reaction, you're taking two light nuclei and fusing them together to make a heavier nucleus. And that's what's going on here, where we're going to take hydrogen-2 and fuse it with hydrogen-3 to make helium-4. And then one neutron gets generated as a side product of this reaction. Here we're asked to calculate the delta E per mole of helium-4 nuclei that are produced in this fusion reaction. And again, we're given the masses of all of the products and reactants that we have here. We'll first use all of these masses that we've been given to calculate the delta M by doing the masses of all the products minus the masses of all the reactants. And remember that AMU can be used interchangeably with grams per mole. So for the helium atom, we'll say that that is 4.00260 grams per mole. Plus, we also have a neutron as a product, so that's 1.00866 grams per mole. Minus the masses of all of our reactants. So we have hydrogen-2, which is 2.01410 grams per mole. And we also have hydrogen-3, and that is 3.01605 grams per mole. And I'm going to say it again here. All of these decimal places matter. So you have to carry all of them through the problem because, you know, even all the way out there in that last decimal place, it will make a difference when you take that value and multiply it by the speed of light squared in finding what the delta E is. So don't just drop out the decimal places here. What you end up finding here is that the change in mass, the delta M, comes out to negative 0.01889 grams per mole over the course of this reaction. So again, if you were to react a mole of hydrogen-2 with a mole of hydrogen-3, the masses of the products that you generate will be lighter by 0.01 grams. And that again doesn't necessarily seem like a lot of missing mass, but that becomes very significant when you take that missing mass and convert it into energy. I'm going to move things up a little bit here and now convert the delta M into a delta E using E equals mc squared. All right, and so our delta E is going to be equal to delta mc squared, or that is to say delta E equals c squared times delta M. The delta E is equal to the speed of light, 3 times 10 to the 8th meters per second squared, times the delta M of negative 0.01889 grams per mole. And once again, don't forget that since we're trying to put things into joules, we have to make sure that mass is in units of kilograms. So that's going to require us to divide by 1,000 here to turn the kilograms into grams. And now we're going to be able to have energy units in joules, and then it's per mole, because we have the per mole from the molar mass down there. That gives us a delta E for this fusion reaction of negative 1.7 times 10 to the 12th joules per mole, which is, again, a pretty substantial amount of energy. I'll remind you that in the course of a day, the entire state of California uses somewhere around 10 to the 15th joules of energy. So if you were to react, what is that, about 1,000 moles of H2 and H3 with one another and fuse them together, you would generate enough energy to power the entire state of California for a day. There is a lot of energy that gets released in this fusion process. Now, you might look at this result and you might have a question here, right? Because what we noticed is that the fusion reaction was exothermic, right? It had a negative delta E, but we also looked at a fission reaction in the previous video, and that was also exothermic, right? Now, when we think about this, like, fission is when you break up a heavy nucleus. Fusion is when you take two light nuclei and fuse them together to make a heavier nucleus. So you would think that these two processes are kind of like the opposite of one another, right? So how could both of these be exothermic? Well, it really depends on the element that you're looking at, and it depends on the thermodynamic stability of the nucleus. We could take a look here at a graph that shows the thermodynamic stability for every single nucleus that you have on the periodic table. And so in this plot, what it has is the binding energy per nucleon. And remember, we talked about how you can calculate binding energies in an earlier video here by determining what the mass defect was for the nucleus. And then to get it per nucleon, you would divide by the number of protons plus the number of neutrons that are in the nucleus. You take the binding energy per nucleon and plot it as a function of the mass number of your isotope. And what you see is that if you were to start with very, very light nuclei, the binding energy increases as you increase the mass number. So what we have is that very light nuclei have relatively low stabilities, And as you move to heavier and heavier nuclei, the stability increases. It increases and it increases and it increases until you get to the most stable nucleus for an isotope on the periodic table, and that will be for iron 56. That's the most stable nucleus of anything on the periodic table. As you continue past iron 56, what you see is that the thermodynamic stability decreases as you go on to heavier and heavier and heavier isotopes. And so these will give you isotopes that are less stable than iron 56. And so what we see from this is that to go to the most stable possible situation of iron 56, lighter elements will tend to fuse together to get you to stability, and heavier elements tend to break up or undergo fission to get you towards stability. And that's the reason why you could have an exothermic process or a negative delta E for fusion when you deal with light elements, and you have a negative delta E or an exothermic fission process when you deal with heavy elements. And so hopefully it all makes sense getting to see in this graph why it is that fission and fusion can both be exothermic, right? Fission is exothermic as long as you're breaking up heavy nuclei and moving more towards Fe56. And fusion is exothermic, and it results in you forming a more stable nucleus when you're dealing with lighter nuclei and moving towards Fe56. Now, nuclear fusion is not just something that's done in a power plant. Nuclear fusion is something that life as we know it on Earth would not exist if it weren't for this. Because nuclear fusion occurs in stars. That is the source of energy that you get from stars. We could think about the sun, for instance. The core temperature of the sun is somewhere around 1.5 times 10 to the 7th Kelvin. This temperature is high enough for you to overcome the extremely high activation energy that is required for you to fuse hydrogen into helium, right? So hydrogen atoms don't just combine together on their own to make helium. There's a huge activation energy and a huge barrier that prevents that from happening. You have to heat the hydrogen up to a very high temperature in order to overcome that activation barrier and then allow the fusion process to occur. And in the core of the sun, the temperature is high enough for you to overcome that barrier where you fuse hydrogen into helium. And then when that fusion reaction occurs, that is an exothermic reaction and a ton of energy gets released. And then that is the energy that is produced by the sun. Now, unfortunately, the temperature in the core of the sun is not high enough to overcome the activation barrier that would be needed to fuse helium into heavier elements. And so eventually the sun will run out of hydrogen and will not be able to fuse the helium into heavier elements. And so then at that point, the sun dies out and is no longer able to produce any more energy. But thankfully, that will not happen in any of our lifetimes. So you don't have to worry about that. However, in larger and hotter stars than the sun, the temperatures can be high enough that you're able to synthesize elements going all the way up to iron 56, which is the most stable. And then at that point, then there would be insufficient energy in order to fuse into heavier elements. So you can get all the way up to iron 56. Now you might wonder, well then how are you able to make elements that are heavier than iron 56? How do we have any element on Earth or anywhere in the universe that is heavier than iron 56? Well, these elements come from supernovas, which are explosions of large stars, and during supernovas, temperature goes way up, somewhere on the order of nearly trillionths of Kelvin. And that will be a high enough temperature for you to overcome the activation barrier to fuse elements together to synthesize very heavy elements. And you can get every single element on the periodic table from nucleosynthesis processes that occur during supernova. I think it's kind of cool to think about where all of the elements that we have on Earth came from. Where did all this matter? Where did all this stuff come from, right? All this stuff came from nucleosynthesis reactions that happened in stars, nuclear fusion reactions that happened in stars billions of years ago. That's where all these elements and all these materials were generated from. I think it's just kind of interesting to see that as an application here. And it's kind of a cool way to kind of finish the general chemistry series. Now, you don't just have to do nucleosynthesis reactions in stars or nuclear fusion reactions in stars. Nucleosynthesis can also be done in a lab. You can do it artificially using what's known as a particle accelerator. In a particle accelerator, you use magnets to accelerate ions to very, very high speeds, nearing the speed of light. And that's going to give these ions a tremendous amount of kinetic energy. And when they smash into other ions with enormous kinetic energy, you're going to have very high energy collisions that are high enough in energy that you can overcome the activation barrier to fusion. And that will allow you to to form new nuclei by doing a fusion process. This allows you to form new elements. For instance, if you were to take the isotope of molybdenum, MO100, and bombard it with hydrogen atoms, what you end up generating is technetium-99, and then 2 neutrons are kind of a side product of this. Technetium is an element that is unstable and it's radioactive. And initially, when the periodic table was being put together, there is no technetium that naturally occurs on planet Earth. And so when people were filling out the periodic table, they had kind of a blank space in there. They knew that an element had to appear in that space on the periodic table, but they couldn't isolate this element because it doesn't naturally occur on Earth. But it was able to be synthesized in the lab, so they were able to fill in that part of the periodic table. Additionally, elements that are heavier than uranium are generally radioactive with such short half-lives that they are not naturally occurring on Earth. And so, how do we get elements that are beyond uranium on the periodic table? They're typically made by performing nucleosynthesis reactions using particle accelerators in labs. You could take uranium-238 and bombard it with carbon-12, and when you do that, what you form is californium-246, right? So this is a synthetic isotope and a synthetic element that had previously been undiscovered prior to doing these reactions in particle accelerators. And that's how you're able to begin generating new elements that have never been discovered before and start filling in new parts of the periodic table. And at this point now, we've filled in all the way up to element number 118 on the periodic table by doing these reactions in particle accelerators. I think it's kind of cool to finish the general chemistry series with this, to see where different elements come from, how you're able to generate them naturally through fusion processes in stars and supernova, and how you're able to also generate them artificially in labs with particle accelerators. And with that, we come to the end of chapter 20. So take a look at this slide here that goes over the concepts that we've discussed here in this chapter. And this brings us to the end not only of chapter 20, but also to the end of general chemistry. I, for one, am kind of happy that we've made it to the end of all of this. It's been a pretty wild ride over the last several quarters. For those of you who have been with me since the very beginning in winter quarter, we've been through a lot together, right? We started off in person winter quarter, and then our lives completely changed in March when we had to start dealing with coronavirus and everything had to move online. And we've been through it all, and we've gotten through it all together. For those of you, who are in your first quarter with me, right, we've been through a lot together, even just this quarter alone. And I'm really proud of all of you for what you've been able to get through over the last several quarters, as we've been going through the general chemistry series. I know that this is not the best way to be learning chemistry, but I think that we've all kind of done our best to kind of get through this as much as possible and to make the most out of what's been a pretty miserable situation. I really do appreciate all of your time. I appreciate your participation in this class. And if you've been in other classes with me, then throughout the entire general chemistry series. And I hope that you've learned a lot about the world around you from the whole general chemistry series here. That was something that always really interested me about chemistry, is that it gives you an explanation for a lot of the physical phenomenon that you see in the world around you. And I hope that you've enjoyed these classes that you've taken here. So with all of that, I want to thank you again for a really great, last 3 quarters in general chemistry. And I wish you all the best of luck on the upcoming midterm exam and on your finals. And I wish you all the best with your future studies as well.